You see people like trying to join. If you could admit them, but maybe I'll start. I'll start now so that we finish on time. It's the day before Thanksgiving, so I don't want to keep you too late. Okay, let me start the slideshow. So welcome everybody. So today the topic is can LLM models plan? So last month we talked about can LLM models reason. The conclusion last time that they can reason, but it's still far from perfect, and then there are still work to be done for for perfect reasoning. For planning is maybe even more difficult than reasoning. Right? To plan, you need to reason, but somehow I think the intuition behind planning is that planning has a longer horizon, has a sequencing of actions. So if reason is not that easy, planning is probably more difficult. So it's I give you a bit of the answer now, but we'll go over the research that has been done. LLM models, no. So I don't need to convince you that they have been at the forefront of the AI, or we call the generative AI revolution. So they perform very well, as you can use, ChatGPT for many tasks, to generate code, translate text, explain the documents as a chatbot, use it as a copilot, or you can use it as personal assistants. They can reason, and as I said, you can still make progress. So can they plan? So we're going to discuss planning, the classical approach of planning. So in fact, there's a huge literature on research area on planning using AI for planning. The different benchmarks and the approaches used using LLM models. So this is the list that we have here. This is a screenshot of the LMC, so LM Arena leaderboard, where the LLM models are ranked, according to what they call the ELO ranking. So in fact, humans are comparing models so interrogate the models and assess the answers. They say I prefer A to B, right? So it's very like chess, when like a player A wins against a player B. So these are the overall ranking. So at the top you have a Gemini, then ChatGPT, and so on. So they are like, I mean, not surprisingly, the privately owned LLM models perform the best. They're the largest and the most expensive to train. Right? So Gemini from Google, ChatGPT from OpenAI, Claude from Anthropic. So what is planning? What is planning? So planning is finding a sequence of steps to achieve a goal, right? Often with some constraints, right? It could be physical constraints or monetary constraints, etc. So here I gave a few examples. So taken from the IPC, so the International Planning Competition. We'll discuss about the IPC later on a bit more. But so these are like annual competition of so scientists, researchers use different algorithms, AI-based algorithms, to solve planning problems. So here it could be the labyrinth. So a robot needs to escape from the labyrinth. So the labyrinth itself can change. So the walls can change and so on. The robot has to come out of the labyrinth. Folding, like very similar to the protein folding problem. Right? So there's one string of a molecule, and have to see how it's going to fold. Right? We're charging robots here. So multiple robots change locations to guard an area. It could be like a museum of like a factory, and they also have to exchange the battery charge, right? Because they're powered, and to be able to move between locations. So what's the optimal plan? How to recharge optimally between the different robots? The illustration here, it is the winner of the last competition. And he's not using LLMs or deep learning or anything. He's using more like classical, what we call like planning algorithms. Okay. So what are they? So this is a whole area of research. So I'm not going to go to give a lecture on this. I'm not a specialist, but you can learn more with in that book from the Russell and Novick textbook on AI and modern approach. There's a few chapters on, I think, chapter 11, maybe chapter 3, on these kind of algorithms. So I'll tell you give you a brief history of where we stand now. I mean, it started in 1957, what we have called the GPS. So you might recognize the name, right? Herbert Simon, Shaw, and Newell. So Alan Newell, so they're like almost the founders of AI. And what they were wanting to develop is a general problem solver. So you just based on the name, you see it's very ambitious and it's very tied to AI, right? And so the idea is to develop a computer program that could solve anything, right? Any problem. So this is really like, so they thought that they could build AI based on this kind of system. So it's using like a means-ends analysis. So they break the complex problems into like sub problems and manageable tasks, and they try to solve the subtask to solve the global task. And we know that today that this kind of approach didn't get close to AI, and the AI that we use today is more like we are relying on neural networks. So not this kind of approach, which is more like symbolic or a programmatic approach, right? Strips. So it's also if you read the literature, this is the 1970s. So something inspired from GPS. It's also an automated planner. So it combines like conditions, operators, states, interest states on goals, and they try to build a plan, which is a sequence of transitions and actions to map to move from state to initial state to final state, right? It is also the name of the coding language because planning problems has to be encoded into like you have to describe it so that a computer program can understand it. It's done in strips, and then we'll see in the next page they have the language called like PDDL. Then tools that you see a lot in this literature. So these are not like strictly planning tools. They're more like search tools. So they go like beyond planning. So the most common problem would be like the traveler problem. Right? The traveler problems that you have to visit X cities, and they have on this let's say in the United States you have to go from New York City to San Francisco, but you have to visit like 20 different cities. You know the distance and what is the optimal path, right? To go there to visit all the cities and minimize the distance. Right? Is the optimal like traveler problem. This problem is we know how to solve it, but this is so there are different paths. Right, so different. You can say it's a finite number of paths between the different cities. It could be the set is very large, and how do you find the optimal path, right? In a finite time, right? And so you have different algorithms, and I think this the textbook from Russell and Novick describes many of them. Many of them could be like greedy, like search algorithms, to try to minimize the distance from one step to the other. Some others are more cost efficient because they use some heuristic. So on top of so they have, so for instance, in that case, for the traveler program. And heuristic could be, well, what is just the distance, geographical distance between, your initial path, your initial point to the final destination, like internet. So not necessarily like the distance using the road or the plane, but just like a geographic distance. It could be a heuristic, and use that try to optimize your algorithms. But there are like many of them, and it's fully described into the book. One algorithm that has been used quite often is called a fast downward algorithms. Downward because it's trying to decompose a problem into sub-problems, so it goes like downward into from task to like a smaller task. So what it tries to do is to translate the planning algorithms into some graphs, right? So there are like two kinds of graphs. One is like transition graphs, so graphs like from moving from one state to another state, right? How like they change, and causal graph. Causal graph means that so causal graph is more general than that. It's more like what the consequence of one action on the effect of this action on the state. What how like an action can change the state. And within the fast downward, he used different search methods that it could be like A-star algorithms, greedy best first search algorithms, multi-heuristic search, etc. So many, so the IPC that I've mentioned in the previous page, organized by the International Conference on Automated Planning and Scheduling, is using many of these algorithms. So you see every year, you see also like who is winning on the kind of algorithms that they use, and very often fast downward is performs very well. When you look at that literature, something that comes up very often is the PDDL. Right? So say the Planning Domain Definition Language. So we saw strips, right? So PDDL is kind of a successor to strips. So it's a standardized language for AI planning. So that these the IPC, that planning competition, is using PDDL, so that you can describe these problems in a unified way, so that everybody is clear about what needs to be done. So what is the initial state, what you are allowed to do, what the actions are, what are the objects. So that it's a unique way to describe a problem. Right? If you just describe it in English is not precise enough, right? To say, you cannot say, oh, I have I need to go from here to there, and then am I allowed to fly? Am I allowed to take the bus, or what are the constraints? So at least with the PDDL, the planning problem is well defined. So they're like a sequence of so what usually PDDL has has two parts. One what we call like domain description, right? So the common elements across all the problems in a domain, and the problem descriptions, what needs to be done, right? So what needs to be done, so I have to travel from New York City to San Francisco, visiting like these different cities, for instance, right? And the actions have to be defined, but what can be done? What are the prerequisites for this action? Right? For instance, if I'm a car, I need to have fuel in the tank. Right? If I don't have gasoline in the tank, I cannot move my car. Right? What is the effect of these actions? Right? So on the car, I can reach a destination. If I'm a robot, I can handle an object and move it. Right? So here, for instance, these are two boxes. These are the domain. These domain description or problem description for a rover, right? For a rover, and we see that you see the different types, the functions, the predicates, the directive actions for moving a rover from one point to another. right? And the condition of the effects of the different actions, what it can do, and the conditions, right? Um, that you need. Um, so for instance, here the conditions. Why, for instance, you have to ensure the rover has enough battery, right, to complete the movement, right? For instance, you cannot go from point A to point B if the battery is not charged, right? So before doing that, he has to check the level of the battery, and if the battery is empty, he has to charge it. And then you have the problem, the definitions, right? With the initial conditions, right? So for instance, the battery has to be charged, and then the goal is to, for instance, reach point B, right? That's a different at a given distance. Right? So PDDL is used for the IPC to define this problem. You see, it's quite important because it's something then the LLM can relate to. Uh, so so do you see this classical approach, right? And then you have to see the language PDDL. And now, usually in AI, we've seen that last month for the for to measure like reasoning. So how to measure like planning skills of LLM models? We need benchmarks, right? So that things are comparable. So for instance, you want to compare Chat GPT-4 with a model from Anthropic, a model from Gemini, and so on. You need a common benchmark to compare them. So. So here, so there's so this is one paper that introduced what they call like PlanBench, right? A planning benchmark. So it allows to use to easily run like some curricula on new domains, right? So here it's run on two domains from so a domain is a given game or like a given task a task to do, right? So before we saw the labyrinth and we saw the folding problems. So here it's using two well-known like domains in IPC, blocks world and logistic. Right? So blocks world is to stack blocks in a given order. Right? You're given a set of blocks, of different colors, or different letters on these blocks, and you have to stack them in a given order. Logistic is to transport like packages within cities or between cities, right? So within cities, it can be done using trucks, and between the cities is use planes. Okay, so these are kind of things. So this logistic problem could be, well, I need to move all these packages from one place in one city, let's say from downtown New York City to a given district in San Francisco, and how do I do it optimally, right? So they are like test cases created for these like two domains, and so the data set of like 26,000 examples or prompts, right? And so they do some experiments on two versions of the GPT of OpenAI models, a GPT-4 and what we call Instruct GPT-3, right? Instruct GPT-3 just means it's a GPT-3 that has been fine-tuned or specialized to follow instructions, right? And GPT-4 is more powerful than GPT-3 and even Instruct GPT-3, right? So here in that in that tables. So they measure the performance across like different different tasks, right? So there are many tasks for block walls and logistic. They can simulate different like number of blocks, the different kind of configurations, and this is what they generate. That's why you see the why it's like over 600, right? And what they do. So the task they correspond to actual planning problems, right? While others correspond to simpler auxiliary like planning task. Okay, so you see that overall, uh, the let's say the plan generation, let's say the first case, right? Need to go over like all of them. So here, like how many tasks the GPT-4 and the Instruct GPT-3 managed to complete, right? And so here, so this is for blocks world, right? Not for logistic. So you said that GPT-4 could complete only 34% of this task, right? So it's less than 50%. And Instruct GPT-3 could perform only like 7%. Right? So it's not great, right? Uh, so this has been done kind of manually, right? These benchmarks. So something more recent called AutoPlanBench, where it was expanding PlanBench, right? So what it does, so it looks at these, so also from the IPC, right? You have this planning competition, planning domains. So they are described in the PDDL language, right? So AutoPlanBench translate these PDDL instructions into natural language problems that LLM models can understand, right? PDDL model, and these models, like ChatGPT, I could understand PDDL, right? Because it is somewhere in the internet, but it's probably easier to translate this into plain English, and it is what it is doing, right? So these different methods, then then you can prompt, right? So you can have like say like a particular like planning the problem described in PDDL. You have the domains and problems, right? Remember that PDDL has like it has like two parts, right? The domain and the problems is what you see here. Then the bench translate this into plain English. Okay, gives an instruction that prompts that you can just give to the LLM models, and then it is assessed across different kind of LLM models. Right? So if you remember from last time when we talked about reasoning, we talked about different chain of thought, prompting, and then you have like things that I didn't mention before, but react, act. These are also different kind of variation of prompting techniques. Could be zero shot, one shot, etc. And then you evaluate. Then you evaluate how good they are at performing this task. And usually the evaluation is done on a sequence of plan, right? They will deliver the plans. For instance, in the blocks world problem, we'll say, well, I take block one, I put it there on the table. I take block two, I switch them, etc., etc. So it'll give you some clear instruction, and you can evaluate to see it managed to do it. Okay. So here you can see for the different problems. So here, for instance, for you see, for instance, the accuracy, right? ACC. The so difference of blocks for blocks world, it'd be 50% accurate. So you get it right in 50% of the time, right? For act and react, but you can do didn't describe this too much, but you can see that it's like 25, 55%. Chain of thoughts, why we did discuss this during the reasoning presentation. The accuracy is only like 30%, right? So you see, it's not great. And these kind of planning, these are like a toy models, really, right? These are not even like real world models, right? Uh, so, the more complex you make these planning problems, the more difficult it becomes on these LLM models, right? So that's more like long-term interactions, or more like if there's a problem with no solutions or dead-end states, that's where you meet states and you have to backtrack. So it gets confused. But most of these problems, because they are taken from the IPC competitions, they are solvable by classical like planning algorithms. that you have described before. Right? So this so it's not great for LLM models. So here, this is another like benchmark. So if you have kids, or I don't know, maybe adults play with this, you have a game called like Minecraft. Right? So Minecraft, you might have seen this before. So these are like an open like video game where you can construct cities, or you meet other agents, and you have tasks to complete. You can do mining, you can cut woods, do all kind of things, right? So this is kind of a nice environment to simulate to explore planning, right? Because you can do it. This is right. I think it's probably free, so you can do like mini simulation and then assess, how good the planning models perform in a virtual environment of Minecraft, right? And you can do like long-term planning because these games don't end. There's no end to these games. You can so it's open-ended. You can do long-term planning. So the benchmark, the MinePlanner, so it's a planning benchmark. So in the Minecraft environment, has 45 tasks and can generate Minecraft task, right, automatically. And then this Minecraft task can be like translating into the planning problems, and can be even written in PDDL language. Okay. And there are constraints in this environment, right? So you can move, right? These agents, they can move. Sometimes most of the time they can just walk, right? They can walk and run, but they cannot fly. For instance, that's limited in their moves. It should be in two dimension on the map. Uh, it cannot. It can only like go to some spaces. It can move, into the four direction, but it cannot move into walls, for instance, right? It cannot. It can jump, but the obstacles have like some limit, so that it cannot jump across like very high walls. Right? So all these kind of constraints that the planning problems has to obey. And then you can like assess any kind of planning algorithms. So here you see that even a classical algorithms, just like fast downwards, even HSP, I think HSP means heuristic search program, something like that. So they have been benchmarked on this, and they don't perform very well. So this is so for classical algorithms it's not easy to solve. So it's even for LLM models it's even more difficult. But this is something that if you one day you come up with in your own research, you come up with you think your LLM models is great at planning this, you can assess it on MinePlanner. Uh, Natural plan is also another benchmark. So before I was saying, these are like this planning exercise were like more like toy examples that you then use for like more like an academic conference, international planning competition. But they're more like toy models, and they might not be very realistic, applicable to real life. So natural plan uh, is a benchmark that gives like more like three realistic models that maybe you can use in real life. So they have three planning exercises. So trip planning, meeting planning, and calendar scheduling. Right? So these are things that you could use in real life. Right? So for the trip planning, here the example is like you visit 3 European cities in 14 days. You can only take direct flights, right, to commute between the cities. You have to stay in London for 4 days, Bucharest five days. You have to meet a friend. So these are things that you might do realistically, right? Okay. Um, and then, so what is the optimal plan? Okay. Between planning, it's the same thing, right? In your job, you might say, okay, I have to go to San Francisco. I have to meet several clients, and these are the travel distance, and these my customers. Like for example, James is available only from one time to from 3:45 to 8:45. How do I plan my time, right? And I want to meet James here like for a minimum of 75 minutes. So these are constraints. So these are realistic planning problems. The last one is a calendar scheduling. Right? Calendar scheduling is something that we face every day. I imagine that co-pilots and so on, they want to solve this kind of task. The scheduling is relatively easier than it's a subset of planning, right? It's somehow easier to solve, but still can be challenging for some models, right? So say I have to schedule. Let's say I'm scheduling the meetup, for next month. But I have some constraint. My co-hosts have to be available. They might be on vacation. Maybe it's because it'll be Christmas. They're in different time zones, so it has to be between that time and that time, so they can. It's not during the night, etc. Okay. So here they also like generate. So here they have these kind of prototypes of plan, trip planning, meeting plan, calendar scheduling, and then they generate the plans based on, so they generate names, times, and so on. So they generate like hundreds of you can hundreds of thousands. Here it had be like 1,600 tasks randomly generated, right? So you can use an LLM to do it, for instance. Uh, for Google Calendar, so for the scheduling problems, and then and then you can use like um, you can use also like Google. You can use Google Flights to find the flight schedules. Google Maps to find location. Okay. So here in that table two, they have been assessing these five models on these like planning exercises. Chat GPT 3.5, GPT 4, 4.0, Gemini 1.5, and so on, and see that some that they're not great, right? That even Gemini 1.5, probably one of the most powerful ones, has about trip planning, performs only like 35% of the task. On calendar scheduling, 49%. Okay. You might be surprised to see this kind of numbers because you have like commercial solutions saying that AI can do scheduling and so on. But it's more likely that that the kind of problems that they generate are maybe more complex than what you might see in real life. At least we hope so. So commercial solutions might work if the problem is not too complicated, more like plain vanilla problems. But if it becomes more difficult, it might be challenging even for commercial solutions. Uh, so this is so here. So we've seen like we cover like benchmarks. So I want to talk about some solutions and ideas how we can use LLMs to solve that. So here it's also like using block walls. So this is a team of researchers from I think from Arizona State University, from Professor Kambapati. So he's an expert in planning. He's a bit critical maybe of LLM models, but has like he has constructive criticism on how to use LLM models. So what he's saying that LLM models can plan by themselves, right? What we've seen in the previous page, right? You just like ask for a plan directly to ChatGPT 4 or Gemini. It fails half of the time. Uh, so it's possible that sometimes when it can solve the problems, uh, it might have seen the problems before, right? Because it has huge data from the internet. The plan could be plausible, right? It will give you a plan. Usually, the LLM models are very good at giving you a plan, but the plan might not work, right? You can ask anything. Usually, because these models are very keen to give you an answer, right? Even if the answer is wrong. So that's why the problem of hallucination, right? So so you might need something that looks plausible, if you use it interactively, let's say in ChatGPT, you might correct by yourself, right? You can see, you can read the plan, say, oh, this is good, this is bad, or this is wrong, I could correct it. So interactively, it's still like usable. You can still use the plan given by a chat model, but you might have to, you might have to override it or to add your own expertise or your own knowledge of what's going on to remove the parts which is not realistic, right? So, so here, what they have, what they're proposing is called like a LLM modulo framework. So I think they, in their area, there's something called SAT modulo. I'm not sure what it is referring to, but this is the name of the model. They use LLM tools to assist in planning, right? So what LLM models are good they are good at generating plausible ideas of plans, right? So they might not be accurate. That's not like, no, they use ChatGPT. They give you like a lot of ideas, right? You can ask. So it's very good at that. So try to leverage the strengths of the LLM models. So models, the planning might not be totally accurate, but it can be the plausible ideas of planning. Another way to have the leverage the LLM models are pretty good at translating. Right? You translate. You've seen that before. They were translating the PDDL language into natural language instruction into English, right? So they are very good. It's very good at that. So is doing that. Okay. So here the modular framework will go over all the details. But what it's doing, so you have a you have a problems, right? And then you have could be a domain experts or like um, an expert or model, a planning models that can give some feedbacks on the plan produced by the LLM models. Okay, so given the problems, LLM models can give like a plan, so the LLM response. And then it goes into a series of what we call like critiques, right? So they different like models to critique the plan from the LLM models, right? So either you can say, well, it agrees with the plan. So in this literature, you can also verify if it's a plan works or not, right? You have like algorithm to verify, to validate a plan. So you can say, well, we agree, it's a valid solutions, right? And then it starts into like it's applied to synthetic data, and it gives a positive answer. Or you can disagree, or you can say why your plan is not working, right? Or you can suggest improvements, right? So it's what they call the meta controller. So it gives like the feedback to the LLM models, and the LLM models so read the feedbacks and regenerate a new plan. Okay, so this is how it is done, right? So the idea is to have critics to assess a plan produced by an LLM model. It could be a verifier. It could verify the plan of the models, or you can give suggestions of the syntax. We said the syntax of the LLM model is wrong, right? It doesn't obey like like PDDL syntax for instance. It got confused or something like that. So you can use it this way. Uh, so here, so the same team, they revisited their work, but in light of the new OpenAI models, right? Especially the recent like OpenAI O1 preview. Right? The one that can talk right on your phone, on the one that thinks. Right? So you have used it. You have used this OpenAI preview in some mode. Uh, it thinks. So it thinks meaning that it takes time to give answers, right? I give you different steps, right? It says so solve something. It tells you why I'm doing this, I'm doing that, and then you wait. So it can take 30 seconds to find an answer. So it is doing some decomposition of thoughts, right? And according to OpenAI, it's reasoning, right? So what they found, so that team, so they said that that OpenAI preview, the one that can think, is much better, right? It's much better than the models from before, right? So for instance, for Block's World, uh, the generic one, it solves 98% of the problems of Block's World, right? Uh, but when they make it a bit more difficult, it's a bit it's worse. So it's like something only like 41%. Mystery wall blocks walls. So there's some variation of blocks walls where you don't disclose all the information about the blocks, for instance, or you primary. So it's not fully informed about the state. But it's still much better than what we have before, like GPT-4 on some, right? So they're still pushing. So they say that, well, O1 on preview is not, it's much better, but it can still be improved. And especially, there's no, you use some plan, there's no formal like verification, the certification that it is good. Most of the time it gives good results, but sometimes it doesn't give good results, and we don't know why, and there's no guarantee, right? And for critical application, right? So let's say you want to send something to Mars, something like that, it has to be 100% accurate, and then and you cannot just count on the LLM models, doing a good job. So there's some so there's still a need for them. So of course they're pushing their approach, right? The LLM modulo approach. So to verify, to have a verifier, right? To verify and certify the plan. Okay. So here, this is an approach, in fact, that has been used, was introduced 2 years ago. So we know that LLM models are pretty good at coding, right? So you can use it for GitHub is using, you have a GitHub Copilot where these LLM models can generate code. And very often the code can be pretty good. Anthropic, Claude AI is also pretty good at coding. So here the idea is that can you use the coding abilities of LLM models to generate planning code, right? So to generate code to solve these planning problems, right? So so it seems that they can, for so here they use like it's an older model, it's called like code T5, but it's not any like coding LLM model for use for coding codecs or even just like Claude AI. Any version of Claude models can be used today. So it will generate a goal-oriented, goal-directed instructions, right? And in term of in codes, and that you can test, right? And how it was done. So they've done it by training the models. So they didn't just use it like this. They trained the models based on some. So here it was like they specialize on one set of problem of the Towers of Hanoi game. Towers of Hanoi game. I know you remember this. So this is a game where you have some rings stacked, and you have to move one ring from the left to the right, right, on some pins, and you can smaller rings can only be on top of a larger rings, right? It's what they call a Tower of Hanoi. So it's only pyramidal, and you have to do an algorithm to do that. So you have like PDDL, you have like the domain on the problems, what to do. Let's say, move all the stacks from the left to the right. They generate solutions using the fast downward planning algorithms, right? And for this fast downward is accurate, is 100% accurate, can solve it perfectly. Right? So they have the truth, right, of these problems. And then they separate into training data and test data, right, that you use in machine learning on AI. And they train the codify the large language model on the training data, and they test it on this, right? So they test it on no, can it complete the plan, or also for they use this rouge and bleu. Rouge and bleu usually you use it for translation, right? So they say does it have perfect recall? Um, um, for instance, so they compare the plan produced by what they call the transformer with the truth, right? And you see like how much how much they overlap. So you have does it have like a perfect accuracy? Does it have like a precision? This is really like precision on recall. Okay. Uh, so so what they find, the samples, when you give like more examples, or what needs the examples, these models tends to learn, how to do it, and they find that it works quite well. But this is not only done on towers of Hanoi. So you can imagine that it might be expensive to do, right? If each new problem, new planning problems, you have to fine tune the models, retrain the models. It might not be like super convenient, but in some environment, it might be interesting to do. Uh, so here, um, this is like another approach. So what you call like a LLM dynamic planner, right? So what they do is so they try to combine so what you call it neural symbolic that integrates large language models with a traditional planner. That's what the traditional planner, like a fast downward, would be a traditional planner. And so what they try to do, so they start from a problems, right? Like in um, let's say in describe in natural language, and the LLM models translate these problems into a PDDL problem language. So there's already like a PDDL like domain has already been defined, right? The environment, but the task is given in natural language. So it could be like the researcher gives the instruction to say, okay, moves this rover, or like here in that case, I know something like about the cooking some potato. So I want to cook the potato, and then so try to do it. So it could be a instruction to a robot, for instance. It could be a embedded AI, it could be a robot. Say, okay, go to the kitchen and cook some potato for me, right? So the LLM will be able to generate the problems in PDDL format, right? We know that LLMs are pretty good at translating problems. They'll be sent into a classical like problem planning solver, right? Like done forward, right? And then it'll give the selection the plan generator will select the plan, and the LLM will give the series could give the series of instruction. If it is the LLM is embedded into a robot, then the robot will follow this instruction, right? So here the LLM is really used as an interpreter, but the brain really is done by the planning algorithm. Um, so maybe skip, or maybe I can go over this one. So there are a lot of ideas, of trying to combine LLMs with Planner. Here, this one is just use the LLM models, right? So, but sequentially on several times, right? So here is using GPT-4, right? And with chain of thought, and so it means that it gives into it describes the different steps, and also as you tell ChatGPT-4 you have to decompose your reasoning and your planning. So So here it's also using some probably these are some classical also planning problems like delivery, gripper, ferry, and so on. I compare GPT-4 with the older model like GPT 3.5 on using without chain of thoughts and so on. Okay, so so they find that the programs generated by GPT-4 in these specific planning domains s- outperform some planners and some other some other models, right? Um, so it suggests that it can be used in some areas, but these are like really like toy models. But the important step is that you query, right? You query the ChatGPT-4 GPT-4 several times, right? First to translate the domain, right? And then you give a summary of the domain, then the strategy, then the plan, and then you try to you validate the model. Okay. Uh, So here it is also another approach. So here I give you the idea, basic idea quite quickly. Here, the LLM models is used to try to rank the different actions, the actions proposed by a planning model. So he said like, is the actions good or bad? And the model is specifically trained to do that, right? So the model is almost used. The LLM model is most used as a heuristic model to rank actions, right? So it's used like heuristic in planning tasks, so different tasks and actions, and the AI models give the evaluations, right? So heuristics is used a lot for planning, for search also, what we've seen before, because they are computationally like more efficient, right? They're imperfect. Sometimes there's no guarantee that you find the answer, but most of the time they find reasonable answer in limited time, right? So the compute time is so LLM models are leveraged to do that. Right? So remember, LLM models are good to find approximative solutions, plausible solutions. You're pretty good at that. They're pretty good at translating from one language to the others. So you have to leverage them like that. It's not that great to find. I think I mean how they are used today. They're not great to find the exact solutions, right, to a problem. Okay, so just have a few minutes left maybe to get questions too. But so in conclusion, planning is a difficult problem. So maybe it's more difficult than reasoning, even with classical methods, right? Classical methods, the ones that we've seen, right, the first few slides, they have limitations, right? The PDDL, in fact, yeah, I did some search, and it's not used that much in real life. In the industry is that maybe there's some variation, but in some limited situations it is used, but there's a limited expressiveness of this classical planning, even of a PDDL, because PDDL you have to describe all these objects, what they can do, the properties, all the actions, and so on, and that set can be huge, right? If you really try to do like a real planning exercise. It assumes perfect information, but in reality, you have limited information. When you plan, you have always like unexpected things happening, right? You plan to send some astronauts to the moon. You have like so many things that can happen, and the planning system might not be aware of that. You might have like environmental violations, right? You might not be able to launch your rocket at a given time or a given day on so. So exploring state space, right? So the number of states. The state means like all these contingency situations could be very, extremely large, and not that planning algorithms, the standard planning algorithms cannot handle. It assumes a deterministic model, right? But things can change, and so it's not uncertainty. So we talk about that. So We might not be all this. You might not know all the states, right, perfectly. The environment is usually static, but the environment can change, right? When you do like let's say we plan to send astronauts to Mars in 10 or 20 years from now, so many things can happen, right? And that you might not have specified today in the state space. So at the end, these classical planning systems are not very super practical, right? It's not maybe surprising that the kind of problems that they solve are very like more like toy examples. So LLM models, we know that they are by themselves. They are no, they struggle to even solve these like toy models, right? But they're making progress. Like OpenAI O1 preview is much better than the previous LLM models because they have that sequential reasoning steps probably, and they're probably doing some search on when they solve the problem. So it's not fully disclosed, right, on how it works. That people are guessing. So how do you improve the planning capabilities of LLM models, right? So you can try, we've seen previously, you can try to connect LLM models with these traditional planning algorithms, but you can leverage the coding capabilities of LLM models, right? So not even the wheels, but we know that LLM models can code, right? So okay, you see if some problems can be solved by code, LLM models probably can do it, right? You can use a hybrid system, right? So the modulo approach on the one when the LLM just models translate instruction into PDDL code. You can use that. People think a lot in terms of LLM models and neural symbolic systems. So neural symbolic systems, they could be planning systems that go beyond that, right? So from the 1950s, people thought, so you could see that the GPS, the General Problem Solver, is kind of neural symbolic system. I didn't go into details into that, but the people who criticize LLM models a lot today, sometimes they come from the linguistic tradition. When you try to understand words, grammar, and so on, this is what is something closer to what they call neurosymbolic. So where words have a meaning, symbols, and so on. In LLMs, words don't have meanings. I mean, they have some implicit meanings. They have these what they call embeddings, but they don't have really a notion of what is a dog, what is a cat, and so on, right? People who are in linguistics, they say, well, LLM models are very limited. You will never reach AGI because they don't really understand anything, right? They're just vectors, but they don't have the concept of, they have those symbols, right? So people think, okay, maybe you should merge the two. Maybe it's possible, but we don't know, right? What is for sure that is, I think this, and we talk about this during the reasoning presentation, that you need external verifiers. So there's something called val in the planning literature, but you need a ground truth. You need someone to be able to tell an oracle to tell the LLM you are right and you are wrong. That your planning algorithm works or doesn't work. You need that, right? So that for to really use it, maybe to deploy it in production. Or you have to be 100% sure that what it is doing is correct, right? We didn't discuss learning because LLM models that we use for OpenAI, we cannot train them. Well, we cannot train them. We don't have access to the training code. We don't have access to the weight, right? So it's not we cannot really train them. But some open source models can be trained. So it means that they can learn, right? They can learn. I mean, today there's some limited learning, right? In the context, in the prompt, you can learn from the prompt, but you can really like revamp the models. So you can imagine that tomorrow, in the future, some models, LLM models can learn, right? Can learn to do planning task, right? Like AlphaZero, AlphaGo learn to play Go, right? So AlphaZero learn to play Go by itself, by playing against itself, right? And improves. So here you can imagine LLM models combined with a verifier can learn to plan, right? Can or the modulo approach have a verifier plus some critiques and feedbacks pose a plan, the plan works or doesn't work, and get critiques and then improves, right? And then improve by itself. And can you do that, then maybe it can reach some superhuman skills in planning. But without learning, it probably is pretty tough to do that. So in conclusion, can LLM models plan? So in fact, basically, it's still work in progress, right? Still far from be able to produce like a perfectly executable plan. It can assist in planning, that's for sure. It can give you some ideas, some good plans, but you need a human override or human supervision to do that, or some critics or some or classical planners to complement what the LLM model is doing. Okay. So I'm going to stop here, stop sharing my screen. I don't know if you have anyone has some questions on or comments on that.
Congratulations on the book.
Thank you.
Is it a physical book?
Yes, it'll be a physical book. Yeah, I mean the ebook
Okay.
will come up first, and the physical books probably come a few weeks after. But you'll be able to.
Okay.
Okay.
I am a commodities person, so I will buy the physical book.
Okay.
And I like to touch the paper and understand better.
Okay. Okay.
It's very nice.
Okay.
Yeah.
So if there are any other questions, I wish all of you like in the US a happy Thanksgiving. I'll talk to you next month. Okay.
Yep. Very nice. Thank you.
Goodbye.
Happy Thanksgiving to everyone.
Okay. Goodbye.